When we think about long-necked reptiles from the distant past, a single image immediately comes to mind. Massive plesiosaurs gliding through Jurassic seas, their elongated cervical series appearing proportionate to streamlined bodies shaped by millions of years of evolutionary refinement. But long before the age of the plesiosaurs, and even before the first true dinosaurs established their dominance on land, another reptile evolved a neck so disproportionate that, at first glance, it appears almost structurally impossible. Its name was Tanystropheus. At first sight, its body seems ordinary. A slender reptile, elongated tail, relatively small head. Yet nearly half of its total body length consisted of a rigid, extremely elongated neck, composed of only a limited number of dramatically stretched vertebrae. Unlike the flexible neck of a swan or the many small vertebrae of a plesiosaur, the neck of Tanystropheus was built from a small series of highly elongated cervical bones, creating a structure that was both long and comparatively stiff. To understand how such an unusual body plan emerged, we must travel back to the early and middle Triassic period, roughly 247 to 237 million years ago. The Triassic world was not yet stable. It followed directly after the Permian-Triassic mass extinction, the most severe biological crisis in the history of complex life. During that event, an estimated majority of marine species and a significant proportion of terrestrial vertebrates disappeared. In the aftermath, ecosystems were simplified, fragmented, and in many regions unstable. Yet this ecological vacuum also created opportunities. Surviving lineages began to diversify, occupying niches left vacant by extinction. Among these survivors were early diapsid reptiles. During the Triassic, they underwent a remarkable radiation. New lineages appeared both on land and in the sea. The oceans, in particular, became arenas of diversification, as several reptilian groups independently adapted to aquatic environments. It was within this broader radiation of early archosauromorph reptiles that Tanystropheus emerged. Tanystropheus is classified as an archosauromorph. This means it belongs to the broader clade Archosauromorpha, a group that includes archosaurs, the lineage that would later give rise to crocodilians, dinosaurs, and ultimately birds, as well as several earlier stem forms. Archosauromorphs are more closely related to archosaurs than to lepidosauromorphs, the lineage that includes modern lizards and snakes. However, Tanystropheus was not an archosauriform and did not possess the derived characteristics that define true archosaurs. Instead, it belonged to a more basal branch of archosauromorphs known as Tanystrophidae. This group included genera such as Longobardosaurus and Tanitrachelos, which displayed varying degrees of cervical elongation. Some possibly related forms, such as Ozimec, were highly specialized reptiles with unusual body proportions, and may even have been capable of gliding, although their precise phylogenetic position remains uncertain. More distantly related archosauromorphs, including Dinocephalosaurus and Gracilicolum, also evolved extremely elongated necks. These forms were not true tanystrophids, but their morphology suggests that neck elongation arose multiple times within early archosauromorph evolution. This repeated emergence of extreme cervical proportions indicates that during the Triassic, certain ecological pressures may have favored such body plans. The largest species, Tanystropheus hydroides, reach total lengths of around 6 meters. It is generally regarded as one of the largest known non-archosauriform archosauromorphs, though absolute size comparisons remain limited by the incompleteness of the fossil record. Its neck alone could measure over 3 meters in length. Yet remarkably, this extreme elongation was achieved with only about 13 cervical vertebrae, each stretched into long, rod-like elements. Biomechanical studies and recent CT-based analyses have shown that these vertebrae were reinforced by elongated cervical ribs, forming a bracing system that likely reduced flexibility. The neck appears to have been relatively rigid compared to that of later marine reptiles. Earlier interpretations suggested that such a structure would have been excessively heavy and biomechanically inefficient. However, more recent research indicates that the neck may not have been as massive as once assumed. Some biomechanical reconstructions suggest that it represented a relatively moderate proportion of total body mass, though exact estimates vary depending on reconstruction models. The skull of Tanystropheus hydroides, revealed through modern imaging techniques, displays features consistent with a primarily piscivorous diet. Its teeth are elongated, recurved, and suited for grasping slippery prey. Smaller specimens traditionally referred to Tanystropheus longobardicus, particularly those from Monte San Giorgio, show an unusual dental pattern. In the posterior portion of the jaws, some teeth possess 3 distinct cusps. This tricuspid morphology is rare among reptiles. Earlier interpretations suggested that these teeth may have been useful for gripping insects. However, later studies have proposed that they may instead have assisted in securing slippery prey such as fish or soft-bodied animals. Interestingly, the larger species Tanystropheus hydroides lacks these tricuspid teeth and instead possesses elongated conical fangs along the margins of the jaws. This difference in dentition may indicate a degree of ecological separation between the two species, with the larger form likely targeting bigger or more active prey. Similar tricuspid teeth are also known in other Triassic reptiles, including the early pterosaur Eudimorphodon and the related Tanystrophid Longobardosaurus. Fossils of Tanystropheus have been discovered primarily in Europe, particularly in what are now Switzerland and Italy, in deposits representing shallow coastal marine environments. These settings were lagoons and nearshore marine systems situated along the margins of the supercontinent Pangaea, particularly along the western shores of the Tethys Ocean. The climate during much of the Triassic was generally warm, with extensive arid regions inland, while coastal areas supported complex marine ecosystems. The presence of marine invertebrates and fish in the same deposits supports the interpretation that Tanystropheus inhabited shallow marine or lagoonal environments. It is generally thought that while it may have been capable of moving on land, its morphology suggests a predominantly aquatic lifestyle. The extraordinary neck of Tanystropheus has long puzzled paleontologists. Earlier hypotheses proposed that it were primarily terrestrial, using its elongated neck to fish from the shoreline, extending its head into the water while keeping its body on land. However, further anatomical studies have challenged this view. The rigidity of the neck, combined with evidence from cranial morphology, suggests that it was more likely adapted for aquatic predation. Current interpretations increasingly favor the idea that Tanystropheus hydroides was a predominantly aquatic predator. It may have swum using its powerful hind limbs, which appear more robust than the forelimbs, possibly contributing to propulsion. Its relatively stiff trunk and elongated tail would have contributed to stability in water. The long neck, terminating in a comparatively small head, may have provided a strategic advantage. By keeping the bulk of its body at a distance, it could approach fish with reduced hydrodynamic disturbance. While primarily aquatic, it was likely still capable of emerging onto land, at least temporarily. Tanystrophids persisted throughout much of the Triassic. However, by the late Triassic, marine ecosystems had become increasingly complex. It is possible that ecological competition contributed to their decline, though direct evidence remains limited. The group disappeared by the end of the Triassic, likely in connection with broader environmental instability during the end Triassic mass extinction. In this dynamic context, extreme morphologies, such as that of Tanystropheus, were possible. Its elongated neck was not an evolutionary anomaly in isolation, but part of a broader pattern of anatomical diversity among early archosauromorphs. Yet unlike later long-necked marine reptiles, this anatomical configuration did not persist. Its body plan was highly specialized, perhaps effective within a narrow ecological window, but ultimately transient. Tanystropheus stands as one of the most striking examples of anatomical disproportion in vertebrate history, a reptile whose neck appears almost structurally implausible, yet which survived and diversified within the coastal ecosystems of the Triassic for millions of years. Although its lineage did not persist beyond the Triassic, it provides insight into a world still rebuilding itself after catastrophe, a world in which evolutionary possibilities had not yet settled into familiar forms.